All right, so I'm going to try this out, see how this works. So basically, what's going to happen, guys, is I'm going to post a video each day of the lesson. On the lesson, of course, will be homework assignment, which will be on the drive, as always. And you guys can work on them, and I'll post a key for all the homeworks as well. Also, you can contact anytime, send an email, and I'll help you guys out with whatever issues you're having, or a message on Remind or whatever it is, and we can look at a problem together. But for now, I'm just going to try to teach like this through a video. So it's our last chapter, or almost last chapter, 1.5 chapters left, and it's chi-square. And our first day, we're going to talk about chi-square test for goodness of fit. So there's going to be 3 different types of chi-square. Right now, we're going to look at goodness of fit. So the following is just an example of something that could take place in a chi-square chapter. So it says some people look a lot like their dogs. Maybe they deliberately choose animals that match their appearance, or maybe they're perceiving similarities that aren't really there. Researchers at USC decided to investigate. They designed an experiment to test whether or not dogs resemble their owners. The researchers believed that resemblance between dog and owner might differ for purebred and mixed-bred dogs. So they take a sample of 45 dogs and their owners, and they photograph them separately. Then the researchers construct 3 pictures, each consisting of one owner and that owner's dog, and then one other dog, just at the random dog at the park. The subjects in the experiment were 28 undergrad psych students, and each subject were presented with the individual sets of photographs and asked to guess and pick which owner was the correct owner of the dog. So, table below shows the results. And the question that they're going to ask, and this should look kind of similar to what we've seen with significance test, is does the data provide convincing evidence, there's that sentence again, of an association between dog breed status and whether or not they resemble their owners? And here are some good pictures of people that do look like their owners. Cool. So anyway, first up, inference for categorical data. So last chapter, we did confidence intervals and significance test for 2 populations, comparing them. I know we didn't get to have a test on that, but that's okay. We'll be all right. I'm sure you guys are very upset. Sometimes you want to examine the distribution of a single categorical variable in a population. To look more closely at that single categorical distribution, we use what's called a chi-square test for goodness of fit. So let's jump right in and see what an example of this looks like. So the company that makes M&Ms is called Mars Incorporated. And they have a color distribution of what they claim. They claim that 13% of all M&Ms are brown, 13% red, 14% yellow, and so on, with the most being blue at 24%. Now, this is something I actually did many years ago. It says my roommate has a giant bag of M&Ms, so I took an SRS, also known as a handful. I just literally reached in and grabbed a handful, and we got the following results. So we got 9 blue, 8 orange, 12 green, 15 yellow, 10 red, and 6 brown. Total of 60. Okay, so here is a single categorical variable, which is color, and we want to see, is there some evidence that these numbers match this distribution, which Mars Incorporated claims. So, if you wanted, we could carry out a significance test for each color individually, but you can see this is going to start to take a little bit of time. So we could say, set your null hypothesis that the proportion of blue, let's assume that it is 0.24, and then alternatively, we can do a test to see if the proportion that is blue, the true proportion, is not 0.24, and then you could do it again. And we could do it with brown. We could say, assume that the proportion that's brown, 0.13, and alternatively, proportion that's brown, not 0.13. Do we have evidence for that? And then we could do it again, and you could do it for each color, but as you can see, this would start to get pretty lengthy. So instead, we come up with chi-square, which allows us to check not individually per colors, but does allow us to check this entire distribution. So, just like in any other test, before we go on, we have to state null hypotheses and we have to state alternative. So for this M&M's problem, we would set a null hypothesis as follows. Null hypothesis. Assume that the company, what they claim, is correct. So we're going to say company's claim of their color distribution is correct. Assume that what they're saying is true. Let's give them the benefit of the doubt, and then alternatively, the company's claim of their color distribution is not correct. And we're going to, again, as always, see if we have evidence to reject the null and say we have evidence in favor of the alternative that what they're claiming is not correct. So to do that, we use a chi-square goodness of fit test. So the idea of a goodness of fit test is to compare what we call the observed counts. That's what we get when we take a sample. So it's to compare the observed counts from our sample with the counts that would be expected if the null were true, which we're going to call the expected counts. So we observed 6 brown, 10 red, 15 yellow, and so on. That gives us a total of 60 M&Ms. Now, if there truly were 13% brown, then we would expect 13% of 60 is 7.8. So 7.8 is how many expected brown we expect to get if we were to take 60. Now, it doesn't make sense because you can't really get 7.8 brown M&Ms out of 60, but it should be close to 7.8. Now, with what's up next? Red, 13% again, so that's pretty easy. 13% of 60 is again 7.8. And then if I carry this on for each color, you get 8.4, you get 9.6, we expect 12 orange, we'd expect 14.4 blue, which, if you add those up, will also be a total of 60. Now, if you look at these more closely, a couple of them stand out to me. Ones that were the most different from the observed, well, I might say yellow and blue, right? Those probably are the most different, maybe orange as well, but these are the ones that are the most different from what we would expect. And we're going to talk about why those stand out a little bit. So the first thing we have is we have a chi-square statistic. And the chi-square test statistic is going to tell us whether or not we have evidence, assuming the null is true, if we have evidence for the alternative. So to do this, we compare the observed counts from our sample with the expected counts. And if the observed counts are far from the expected counts, then that means that we have good evidence that the null is not true. But how do we measure that? Well, we have what's called the chi-square test statistic. Now, the symbol for it, it's like a script X with a squared symbol, equals the sum of the observed minus the expected squared over the expected. Sometimes I just like to write it as the sum of O minus E squared over E. And mostly the calculator will do this for us, but we should be able to see where the parts of the chi-square test statistic come from. They're called contributions. We're going to see which color contributes the most to the chi-square test statistic. So, for example, here, calculate the chi-square test statistic for the problem that we just had, and you can see all our observed colors and all our expected colors are all here already. We have the formula right over here. So the formula is chi-square equals the sum of the observed minus expected squared over expected. So this first time I'm actually going to do it by hand. It's going to be a little tedious, but that's okay. So we get chi-squared equals, first off, let's do blue first. So this is for blue. And we get observed minus expected squared over expected. Now, one thing I didn't bring up, which is actually kind of important, you'll notice the chi-square test statistic will always be positive because even if you get a negative difference up here, when you square it, it will become positive. Plus, so it's a sum of all of these for all 6 colors. So you can see how this starts to get a little tedious. So next up is orange. So for orange, we have observed minus expected squared over expected plus green, which is observed minus expected squared over expected plus, and we're going to do this 3 more times for the other colors. Now, the chi-square test statistic we get from the blue comes 2.025, plus from the orange comes 1.333 repeating, plus from the green, test statistic is 0.6, and then we didn't say this one, but yellow comes out to 5.186, red comes out to 0.621, and brown comes out to 0.415. Now actually, I'm going to go back here and show the yellow to show what's going on here. So for the yellow, remember we kind of said the yellow was pretty far apart from the observed and the expected, but when you get observed minus expected squared over expected, there's a reason that this contribution to chi-square, 5.186, is the largest out of all 6 colors because the difference of the observed and the expected was the largest. Now, when I add all of them up, we get a chi-square test statistic of 10.18. Right, so we'll keep that in mind for now. So next up, what are chi-square distributions and what do they look like? So they're different from normal curves and t-distributions, and it's called the chi-square distribution. And there's a condition that we must have before we're allowed to use chi-square, so it's something we're going to eventually have to check, and it's that in order to use a chi-square distribution, we must have all of our expected counts must be at least 5. Which, was that true? Yeah, we were good there. So, similar to t-distributions, chi-square distributions differ based on each possible value of degrees of freedom. And to calculate the degrees of freedom for goodness of fit, we have degrees of freedom equals the number of categories minus 1. So in this case, there were 6 different colors. 6 minus 1, 5. What does a chi-square distribution look like? Well, they are very different based on the number of degrees of freedom. So first off, chi-square test statistics are always non-negative. We talked about that, so you can't get anything less than 0. The mean of a chi-square distribution is equal to the number of degrees of freedom. When degrees of freedom are greater than 2, the peak of the chi-square distribution density curve is at degrees of freedom minus 2. So for example, if you see here, degrees of freedom is 8. That means the highest point of that is at 6. And when degrees of freedom is 4, the highest point is at 2. Not really important to know, but good to... They won't test you on that. They won't X that, although maybe in a multiple choice, but you could always graph it, I think, in your calculator and try to figure that out. So, they're always skewed right. However, the higher the degrees of freedom, the less skewed it becomes, which you can kind of see. When degrees of freedom is 1, it's very skewed right. Degrees of freedom 4, it's skewed right. Degrees 8, it's skewed right. It's still going to go off, but the higher they are, the less skewed it is. Now, how do we calculate the p-value manually? So we have a chi-square test statistic. Remember, it's chi squared, and we got 10 point, I believe it was 18. So to calculate that, that means, well, first off, a couple of things about that we forgot to mention. Our degrees of freedom here, how many colors did we have? 1, 2, 3, 4, 5, 6. So it's actually incorrect. I screwed up. Our degrees of freedom should not be 3, so this number actually does not match. But you get a chi-square test statistic, so chi-square is 10.18. Degrees of freedom are 6 minus 1, that's 5. Which means if I think about what the curve looks like, 1, 2, 3. This will be the highest point. It's a terrible curve. And if we want to calculate the probability of being a test statistic of 10.18 or more, somewhere out here, we can calculate this probability. So to do that, we would use a chi-square CDF. And you're going to put your lower bound as 10.18. I don't know why I have it rounded there, 10.2. Upper bound 99999, degrees of freedom not 3, we said degrees of freedom 5, and then we would calculate the p-value. That is, again, the probability of getting an observed difference of what we got or greater, assuming that their distribution was correct. Now, with that p-value, I guess it would depend what alpha was, but let's say 5%. With this p-value here, 0.01694, we would reject the null and say we do have evidence that their distribution of what they claim, those percentages, was not correct. But we'll do more with that tomorrow. So here's a type of problem. We'll just look at one more example. A company claims that each batch of its deluxe mixed nuts contains 52% cashews, 27% almonds, 13% macadamia nuts, 8% Brazilian nuts, and to test this claim, instead of checking every single nut that they make in the company, they decided to just take a sample of 150 from the latest batch, and they matched to see what happens. So you can take a look here. Cashew was 83%. Cashew were 83 nuts. Almond was 29. Macadamia 20, and Brazilian 18. And then they want us to state appropriate hypotheses and calculate the expected counts for each type of nut. So they're not making us get the test statistic, just really set it up. So first off, let's state our hypotheses. So we have a null hypothesis here. The company's distribution for nut types is correct, and then we'd look for alternative evidence that the company's distribution for nut types, we're trying to find evidence, is not correct. So that's part A. Part B, calculate the expected counts for each type of nut and show your work. Now, a couple things. They're not going to give you this table, but you should make a table like this. So we have cashew. The observed number was 83. They claimed 52% were cashews, and there were 150 total nuts. So we would have to calculate 150 times 0.52, and we would get our count. Let's see what we, come on, let's do a little. So 150 times 0.52, that would be 78. Then we have almond. We observed 29. They claimed 27% almonds, so 150 times 0.27, 40.5. Then we have macadamia. We got 20. They claimed 13%, so 150 times 0.13, 19.5. Pretty close. So far, almonds are way above, though. Brazil, 18. They claimed 8%, so 8% of 150 is 12. Keep note, if I added these up, they should both add to 150. Cool. Okay, guys, so basically now, you can try tonight's homework, 1 through 4. It should be just calculating expected counts. It might have calculating a chi-square test statistic, and if so, just follow the lead, what we did here. Observed minus expected squared divided by expected, and do that for each color. Now, one thing we didn't talk about yet in this is for both of these problems, the distribution claims, let me find it, sorry, are not evenly distributed. Some problems you should just assume that things are evenly distributed. In that case, if there are, for example, 4 different colors, you would expect 25% of the total to be each color, or something like that. That might come up in the homework tonight, and it will definitely come up in problems tomorrow. Same thing for the nuts problem. This distribution was not evenly distributed. It was proportionate to these claims, sometimes it could be assumed they're all evenly distributed. In that case, you would take 150 and multiply it by 0.25 to see what the expected counts are, but that did not happen here. Okay, so try the homework tonight, and then tomorrow we'll move on to more formal chi-square goodness of fit tests. Don't forget, any questions you guys have, just send me a message on Remind, or you can email me, either one, and I'll be around and I can help you guys out. Cool. See you guys tomorrow.